Hello guys, I hope you have been well. So welcome back. Today we want to do elastic constant calculation using Castep academic. So make sure that you have watched the previous tutorials, especially the one on how to compile, because you must have compiled this and have installed Python from the instructions. So if you did not know some of the commands that you are typing, you are installing Python. So now to download the files that you need for elastic constant calculation, please go to this website, and then after you go to this website, GitHub, so I'll put this link in the description. So you'll get to this link. Now click here, download zip. Once you download the zip file, copy it to your folder, to your working folder, to the Castep folder, the one that we have been working on. So copy to the Castep folder. So come here, copy to this folder, to this root folder, local disk C, Castep, copy it here. As you can see, mine is here. Now extract these files. Once you extract them, you'll get this folder extracted. Now what you need to do is to add the path to this. So we must have this path installed already. We need, the most important is generate strain and elastics. These are the two commands that we need in our path. So we must add the path to this folder in our Ubuntu. So as you can see, in my case, echo, I have already added them. So to add this to your path, you must be in your home page or in your home profile of Ubuntu. So type nano.profile, like that, you'll get this. So scroll down to the bottom. From the previous tutorial when you were compiling Castep, we have these three paths, export paths. We have K-point grid generator, we have MPI and serial. Now you need to add this other path, MNTC Castep elastic constant master. So you just need to copy this line path, of which I'll put it also in the description. So now we do that. Once you add that, please press Ctrl X to exit and make sure you save it. Now restart Ubuntu so that it can recognize this path. You need just to restart it. Now the next thing that you want to do is to get our input files. Now we need to create our working folder in the Castep. So my working folder here is titanium elastic. So, and I've used my generated input files from Material Studio. So I had calculated the geometry optimization, and then I realized that I was not recording anything, so I have to restart this again. So I just need the cell file, the param file, and the PBUSP, and this other folder, I need them. So just delete. Now the next thing that we need to do, we need to watch the previous video. I'll put the link to that video on how you get the input files from Material Studio. Now I want us to compare some few things. If you take a look at this cell file from the one that I have customized and I have edited, and this one is from Material Studio. So the one from Material Studio, it's very lengthy, so make sure that you reformat yours to be like this. How do you know these points? You get them when you're choosing the K points in Material Studio. Now mine is 995. So in Material Studio I got these points, but the problem is when I was trying to run the elastic constants using Castep, I was getting some few errors. Actually not few errors, it was not starting the calculation because of the format of this file, because Material Studio has a slightly advanced compiler in comparison to our Ubuntu one. Now make sure you also reformat like this. Why did I reformat like this? Because if you go to the tutorial of elastic constants, you can see that this format of this example of titanium dioxide, TiO2, you see that this format resembles my format. So make sure that you have a format like this. The only difference is that I have this block species pot. It's just because I'm using ultra soft pseudo potential, which is more accurate and faster, especially for very big systems. Now the next thing that we want to do, why I like to use a Material Studio to, especially the param file, is because it gives me room for so many parameters that I want to customize. So if we open this, you can see that my param file has so many parameters, and it gives me room for so many things. Even the geometry method, linear, LBG, LF, LB, that one, this one. So you can use BFGS or linear. So linear is good for very large systems when you're working with very, very large systems, but all of them are okay. Now, make sure that you have this, and make sure you have copied this USP file here. Now, the next thing that you want to do is to migrate to the folder. Now we are in step 3. Now, I am sure that now step 3 you have already done it. You have copied the cell and param file to the titanium elastic folder, and now we need to migrate to the folder that we need. Now we just need to type cd mnt c Castep, like that, and then cd. Make sure that when you're naming your folders, they don't have spaces. Don't space them, you'll get some errors. Now type ls to see if we are in the correct folder. Yes, we are okay. Now the next step now is to do the geometry optimization, the normal one that we have been doing. So now we do Castep. Now we start with MPI, run Castep.mpi ti, like that. Once you see it like that, now it's starting. Now we wait. Now our calculation has completed successfully. Now we have completed step 5. Now we go to the folder, our working folder, and now we need to open this file and see. Yes, it has completed, and our lattice constants, yeah, we are okay. So 2.960 and 4.668, which is very, very good. Now we close this. Now the next thing now is we need to calculate the elastic constant. For you to calculate elastic constants in anything, any material, you need the Cij. So the Cij files, we need them. Now to generate the Cij files, now we need to use the following command. So we write generate strain py. So you can just come here, copy this, paste. Now as you can see, in my case, generate strain, this is my cell name, titanium. So if you have renamed it anyhow you want it, like in full titanium, make sure it's like that. So once you press enter, you'll get these strain patterns, and if you come back to the folder, you have 11 to 26. Now the next thing now is to calculate geometry optimizations on all of these ones. So I'm going to show you one, and then I'm going to fast forward on all the others. So now this is how you do it. You just come here, just write the normal Castep MPI, and then instead of having this titanium here and preventing any errors, just come, click these ones, copy this, come here, delete this one, and then just right click like that. You are safe. Press enter. So now we wait. So as we wait, we can take a look at this paper which performed elastic constants. So calculations. So there is something that we need to check here. Always refer to your papers. So as you can see, these are the important C11, the C files for hexagonal systems. We are working on titanium, so these are a HCP crystal structure. So we have to follow this pattern, but we'll do all the calculations, not only for one, we'll do up to all the calculations, that all the files that have been generated. Now to do this very, very fast, press up or arrow key up on your keyboard like that, and then delete this one, press number 2, enter like that. So you don't need to come and edit again, just press up, change number 2, and so on and so forth. So yeah, so now our calculations for the CIJs have completed. So we have done 1 1 all the way up to 2 6. So now the next thing is to get the elastic constants. Now what we do, we just copy this, copy, paste. Please remember that you must make sure that this is the name of your seed name, titanium, so, or TI. So press enter. So it has completed. So as you can see, we want to get our final elastic constants. So these are the final CIJ matrix, as you can see, but unfortunately I don't know how to save it. So the best thing maybe is to take a screenshot, and as you can see, we have some few errors. I don't know why we have some few errors or warnings. So but the results are like this: 190, 190, 188, 43, 43, 51. Let us compare this to the published work, and then we see how close or how far are we from. So let's look at this work. So we have C11. So this depends, because these calculations are carried at 0 kelvins. So we can check at 4K. So 176, this is published. So we have 190. Also C12. C12 is this one, not this one. Please don't confuse. So C12 is 86. So here we have 87. Yeah, pretty close. Good. And now we have C13. We have 70.76. Here we have 68 and 69. That is good. That is good. And now we go now to 33. 33 is this one, 188. Here we have 191 and 182. So please remember, this is at different temperatures. And now we have 44. C44 is this one. So we have 47 and 51, as you can see here. And also published from VASP code, we have the values as shown here. So 66 is here, 44. 44 and 55 is the same. They're usually identical. And C66 is usually, I think it's a sum or a division, I don't know, according to this paper. Yeah, it's C11 minus C12, but normally the independence constants of HCP are C11, C12, C33, C44, and I think that's enough, because C66 is usually an average. It's a function of C11 and C11 and C12. So those are the independent constants. We have 5 independent constants. So this is how you do it. I would advise you to take a screenshot of this, because I don't know how to save it. Don't ask me how to do it. If you know how to save this file into text, there are some commands here on how to do it, but I tried this, but I could not do it. So, and also we have the final bulk modulus of our titanium. So we have 114. So this is void. So the best one to use is Hill. Hill is usually the average of these two. So we have 114 plus or minus 1.9, and then we have the shear modulus of 50. So Poisson's ratio, we have these ones in X, Y, Z, and then we have Young's modulus. So all of this, I think we are pretty much okay. So this marks the end of this tutorial. Please just do more practice, and these things are not hard. It's just that you need to do more practice and to refine your skills. Yeah, if you like this work, please consider subscribing and sharing the video. Thank you.